your true potential. Marwadi University. Discover you.
World-class infrastructure, diverse faculty, libraries and labs, 9,000 students from 31 countries enrolled in 32 courses. Join Marwadi University. Discover a foundation for life.
Marwadi University. A place where the library doesn't sleep until you do. Playgrounds that never tire until you run out. Laboratories that continue to innovate with you. An amphitheater that encourages your talent when no one else does. Hostels where you will find rooms for comfort. A placement cell that nurtures and makes you future ready. Classrooms that have its arms open for you. A faculty who is your friend, philosopher and a guide. A campus that is nothing less than a home for you. A university that will always be focused on your development, your growth and your success. Feel the positivity. Witness the development. Discover your true potential. Marwadi University. Discover you.
World-class infrastructure, diverse faculty, libraries and labs, 9,000 students from 31 countries enrolled in 32 courses. Join Marwadi University. Discover a foundation for life.
Marwadi University. A place where the library doesn't sleep until you do. Playgrounds that never tire until you run out. Laboratories that continue to innovate with you. An amphitheater that encourages your talent when no one else does. Hostels where you will find rooms for comfort. A placement cell that nurtures and makes you future ready. Classrooms that have its arms open for you. A faculty who is your friend, philosopher and a guide. A campus that is nothing less than a home for you. A university that will always be focused on your development, your growth and your success. Feel the positivity. Witness the development. Discover your true potential. Marwadi University. Discover you.
World-class infrastructure, diverse faculty, libraries and labs, 9,000 students from 31 countries enrolled in 32 courses. Join Marwadi University. Discover a foundation for life.
Marwadi University. A place where the library doesn't sleep until you do. Playgrounds that never tire until you run out. Laboratories that continue to innovate with you. An amphitheater that encourages your talent when no one else.
Sir.
Yes, sir.
Sir. Principal, sir. Okay.
Yes, sir. Now we can start.
So a lot of background noise is coming.
Now it's fine, sir. Respected Principal, sir, of both the departments, Faculty of Pharmacy and Faculty of Science, faculty members, my dear students, and all the participants, good morning. I, Dr. R.P. Burman, would like to welcome Mr. R. Girijan, sir, as a resource person for second day of a webinar on gas chromatography and mass spectroscopy basics and application. A similar instruction for participants to ask their queries through chat box only during the session. The resource person will address all those queries in question answer session reserved at the last 20 minutes after today's deliberation. I, Dr. R.P. Burman, once again would like to invite Mr. R. Girijan sir to take over the session. Sir, over to you.
Thank you, sir, and welcome all the participants to the second day of this webinar session. Sir, I am audible now? Hello?
Yes, sir. Yes, sir.
Okay,
You are on.
okay. So this is in continuation with what we had yesterday. We had a very brief discussion about gas chromatography as a technique, the instrumentation, applications, and we saw the different sample introduction system, different types of detectors, and various types of applications where GC can be utilized. So before I directly start with mass spectrometry, I would like to show one single slide pertaining to GC. I mean, everyone now know GC is a separation mechanism, and any separation mechanism involves two different phases. One is a stationary phase and one is a mobile phase. That's a very, very fundamental requirement of a chromatography system. Now, based on the type of mobile phase and the stationary phase, chromatography techniques can be classified into various types, and that's what I wanted to show you now. This is a simple classification of chromatography systems depending upon stationary phase and mobile phase, and what is the principle of separation and what is the technique called as. Number one, mobile phase is a gas, inert gas. Stationary phase is a solid. Principle of separation is based on adsorption mechanism, and the technique is known as GSC, gas solid chromatography. Yesterday also I had a brief discussion on this. And again we have a mobile phase as a inert gas. Now stationary phase is a liquid, is an organic liquid, and the principle of separation is based on partition, and the technique is termed as GLC, gas liquid chromatography. So we have two different types, gas solid chromatography and gas liquid chromatography, and the stationary phases are only different. Mobile phase is same. Coming to liquid phase, we have a liquid mobile phase, we have a solid stationary phase. Again, the principle is based on adsorption, and it is called liquid solid chromatography. Those who are very familiar with liquid chromatography, you must be knowing about, say, for example, silica column. It's a fine example of a liquid solid chromatography technique, silica column. Then we again have a liquid mobile phase, and stationary phase is going to be a liquid, and principle is based on partition, and the term, the technique is LLC. Like GLC, it is LLC, liquid chromatography. And that's the one which is more popular, more versatile, more utilized. We have a liquid as a mobile phase. We have a porous polymer as the stationary phase. The principle is based on size exclusion. That is separation based on the size of the molecule. And the technique is known as SEC or GPC, size exclusion chromatography or gel permeation chromatography. It's a very, very important technique, especially in the field of polymer chemistry, to find out the average molecular weights of polymeric materials, the molecular weight distribution, polydispersity, lot of applications. So it's a wonderful technique. We have a liquid as the mobile phase. We use a ion exchange resin as the stationary phase. And the principle is ion exchange. Either it can be cation exchange or anion exchange. And the technique is known as IEC, ion exchange chromatography. Lot of wonderful applications for this technique. And the last one, most of the students also must be doing, we have a liquid mobile phase. We have a thin plate of either aluminum or glass coated with a uniform layer of silica. And the principle is based on adsorption, and everyone knows the technique is very simple technique, thin layer chromatography, TLC. Now TLC has become also automated. Now we even talk about HPTLC. It's a very costly technique. But TLC is still utilized as a basic screening technique. I am not underestimating the power of TLC. TLC is a very good screening technique to have an initial understanding of the type of the composition of a sample. So these are the various classification of different chromatography techniques based on mobile phase and stationary phase. And now we will directly go to mass spectrometry. Yesterday, when discussing about gas chromatography technique, we said there are a lot of detectors available for a GC system. GC is ultimately a separation mechanism, and there is a detector which has to detect the sample compound that is coming out of the column. So basically, it is for the detector is designed to detect the compound and give a signal. Similarly, so when yesterday we saw there are different types of detectors like FID, ECD, FTD, FTD. Many detectors are available for DC. They are all collectively called conventional detectors. They are very powerful, absolutely no doubt. They are very, very powerful, and they can even a detector like electron capture detector can go to even very, very low levels of detection for electrophilic compounds. So sensitivity wise, there is no issue. They're all very powerful. But the problem comes when the sample is to be identified, qualitatively identified. All these detectors, conventional detectors, what we discussed yesterday, they're all very powerful, they're all very sensitive, but they lack in one aspect, that is they cannot reveal the identity of the compound that is coming out of the column. That's a drawback. And that's a very simple reason why we require reference standards in the case of GC as well as LC to find out qualitatively what is the compound. If the reference standard is not available, we cannot identify, we cannot establish the identity of the compound. We can get a separation, we can get a very good sensitive peak, but we do not know what is that peak. For that, we should have reference standard. And reference standard is also to be analyzed under the same condition as the sample. Then we need to compare the retention times, and if the retention times are matching, then we say the compound is identified as that particular standard compound. So that's a normal, even today it is followed in industry also, even though it is not a very foolproof method of identification. It's a qualitative identification technique based on retention time matching. It has got certain drawbacks also, but that is the one which is followed even today by many people in industry. Now, when we come to mass spectrometry, we have got so mass spectrometer is nothing but a detector for GC. It has nothing to do with separation. It is a detector for GC. Whatever is coming out of the column, it will come to the mass spectrometer, and the mass spectrometer is going to give a signal. Additionally, what is the advantage of using a mass spectrometer here is it has got the capability to identify the compound, qualitatively identify the compound without the requirement of a standard. That's the biggest advantage. That's a place where a mass spectrometer is going to score over all the conventional detectors what we have seen yesterday. So when we talk about advantage of mass detector, MS detector has got a very, very distinct advantage over all the conventional detectors in GC. While all conventional detectors provide good sensitivity, they fail to identify the separated sample components on their own. That means they have no capability to identify the compound on their own. That's a drawback of the conventional detector. But sensitivity is wonderful. There is no issue. So identification will remain the responsibility of the user. You have to identify the compound yourself with the help of authentic standards. Now, you imagine a situation where you are trying to analyze a very complex compound like a perfumery compound or a very complex hydrocarbon sample or an environmental sample where so many, maybe a food flavoring compound where so many peaks are going to be going to come, where are you going to get all those standards? It's very difficult for us to get standards for all those separated compounds. It's going to be, it's a Herculean task. So that means we may not be able to identify many of the compounds in a multi-component sample system when we are trying to analyze the sample by GC. Sensitivity, yes, we will get, but we are not, we can only take a fingerprint and we can say this is a fingerprint of my sample, but I do not know what are those separated compounds because I don't have the required standards. On the contrary, if you try to analyze the same sample on a GCMS system, most of the separated compounds will be identified by the mass spectrometer, and where you are not going to use any standard. That's a major advantage of a MS detector over all the conventional detectors. So an MS detector, on the other hand, can carry out a sensitive analysis. Sensitivity, you are going to get at par. There is no issue of sensitivity. So you can carry out a very sensitive analysis like all other conventional detectors, along with a positive qualitative identification without the requirement for an authentic standard. And that's the biggest advantage. So that is the reason why today when you go to any of these perfumery companies, industries, perfumery companies and all, you will find they are using most of the time MS only, GCMS only, because they cannot afford to have an identification. When your sample is going to give 100 peaks or more than 100 peaks, how are you going to identify all those by a conventional GC? So that is the reason why they try to use a GCMS, where with the help of a mass spectrometer, most of the separated peaks can be identified. Okay, and the identification is taking place on the basis of mass spectrum. That's what we are going to see how it happens. Now, what is mass spectrum? It's a very simple definition of mass spectrometry. Sir, am I audible? Okay. Hello?
Yes, sir.
Yeah, okay. So we are coming to a very, the basic definition of mass spectrometry. What is mass spectrometry? The basis of mass spectrometry, in short, we call it as MS, is the production of ions that are subsequently separated or filtered according to their mass to charge ratio and then detected. The resulting mass spectrum is a plot of the abundance, the relative abundance of the produced ions as a function of the M/Z ratio. So for the students to understand a better way, I will just explain this. So the basis of mass spectrometry is the production of ions. That means you, by reading this sentence, you understand that sample has to undergo ionization. That's a very basic requirement for a sample to be identified, to be analyzed by mass spectrometry. The sample has to undergo ionization. That's a basic thing, basic requirement. So ions will be produced. So when the sample undergoes ionization, ions will be produced in the sample molecule, and different ions will be having different mass numbers. It's like this: when you suppose you have a glass bottle in your hand, you drop it down. What will happen? The glass bottle is going to be broken down into pieces, and you will get plenty of pieces depending upon what is the force with which the glass bottle is going to hit the floor. You'll have different types of pieces. Some pieces may be very small, some pieces may be medium size, and some pieces may be large also. So every piece, the weight will be different. The same thing happens in the case of mass spectrometry. When the sample molecule undergoes ionization, the molecule is going to be broken down into pieces. That's the process of ionization, and we call it as fragmentation of the molecule. The molecule, in any way, the molecule is going to be broken down, and various ions or pieces of the molecule will be formed, and each ion will be having a separate mass number. So you get a mixture of all this, and they are all to be separated. When you are having a mixture, they have to separate it, and they are all separated on the basis of mass number. What we call as M/Z ratio. We separate it on the basis of mass number, and all these fragments, all the ions, all the pieces are transferred to the detector, and the detector is going to give us a output, and that output is what is known as mass spectrum of the compound. So the output that is coming from the mass spectrometer is the mass spectrum. And what is the mass spectrum? The resulting mass spectrum is a two-dimensional graph. It's on the x-axis you have the mass number. Normally in simple terms we call it as AMU, atomic mass unit. The mass number that is plotted on the x-axis, and on the y-axis what you find is the relative intensity, or other term is relative abundance of the ions produced. So when a sample is fragmented, some of the ions are produced in larger proportion and some of the ions are produced in lower proportion. It is not same. That is the percentage of ions that can vary. So the proportion can vary. So what we try to plot on the y-axis is the relative abundance or the intensity of the ions produced, that is plotted on the y-axis, and x-axis we have the AMU. So that is a two-dimensional graph, and that forms that is the mass spectrum of the compound. So please understand that mass spectrum of a compound is the fingerprint of the compound. That means if I have a compound molecule, X molecule, the whatever mass spectrum the X molecule is going to produce is going to remain its fingerprint. That means that mass spectrum can be reproduced only by X molecule. If I take Y molecule, the mass spectrum is going to change. Maybe the fragmentation pattern will change, the intensities of ions can change, the relative ratios ion ratios can change, so many things can change. That means the compound, what produces the mass spectrum, and that mass spectrum remains its fingerprint. That's the reason why we are able to identify the compound based on that mass spectrum. So in the case of when we go for a GCMS analysis, the identification of a compound is based on the mass spectrum of that particular compound. Retention time has nothing to do with identification in the case of GCMS. And retention time is what we use in the case of normal GC. Comparing of retention time, standard and sample. That's why we try to identify a compound in a normal GC. But when it comes to GCMS, we are going to identify the compound based on mass spectrum and not based on retention time. So this is the what you call the simple definition of mass spectrometry. Now, basic requirement for a sample to be analyzed by MS, the sample has to undergo ionization, I've already told you. And there are different techniques of ionization. That is what we are going to see a little bit in detail now, going forward. Now, the objective of carrying out a GCMS analysis. Now, suppose you have a GCMS in your lab. You are getting different compounds for analysis using a GCMS technique. And what is the objective? What is your objective of carrying out a GCMS analysis? Number one, see, when you are having a GCMS system, it's a hyphenated technique. We are one side we are having a GC, and one side we are having a mass spectrometer. Both are connected with the help through an interface. And mass spectrometer is always under high degree of vacuum, and GC is always open to atmospheric pressure. So you are connecting two different systems, one which is open to atmospheric pressure, that's your GC side, and one which is kept under vacuum, that is your mass spectrometer side. And both are connected through a interface. Okay, now when you are having a sample which contains more than one compound, the separation is to be achieved first, and the separation is the responsibility of the GC, not of mass spectrometer. Mass spectrometer cannot separate compounds. It is to be separated by the responsibility of the GC column. So the sample is to be introduced into the GC. You have to use the right type of column. So here also I am re-emphasizing column selection becomes very, very important. It's very critical. Unless and until you select the right type of column, you will not get the right type of results even in GCMS. So column selection becomes very, very important. So introduce the sample into the GC, that is goes to the column, separation takes place, and when the sample comes out one by one, when it comes out of the column, it enters the mass spectrometer, and then the mass spectrometer has the capability to identify that compound. So what is your objective? Number one, separation and identification of a given sample, qualitative analysis. So if you are having a sample, maybe a pharmaceutical sample or a perfumery sample or any other sample, which contains more than one compound, maybe 5 compounds, 10 compounds, whatever it is. First of all, you should get a clean separation using the right type of column. And then subsequently, having got the required separation, all the separated compounds should be identified, qualitatively identified. This is your objective number 1, separation and identification of compounds in a given sample, and simply called as qualitative analysis. That's priority number 1 or objective number 1. Second objective, quantification. Now you got a well separation of all the compounds. You have identified all those compounds. Now the second objective is you want to find out what is the concentration of each of that separated compounds. So that means you need to quantify all those compounds which are separated. So quantification of a target component in a sample. Probably you may not be wanting to quantify all the compounds in the sample. You may be wanting to quantify maybe only 1 or 2 or 3. I mean, your target compounds. So that is objective number 2, quantitative analysis. And then the third one is a high sensitive residue analysis. It has assumed a lot of importance in today's world. Today we talk about residue analysis. You think of your food products, whatever you drink, whatever you eat. I mean, we are all, taking different, so whatever we take, whatever we consume, all these products, all these food products may contain pesticide residues. I mean, it's a global problem today. Everyone knows about it. Okay. So when you are talking about pesticides, I'm just taking pesticide as an example. There are so many other things also. So when you talk about residual pesticide, these are all present in very, very, very small quantities. Maybe even the concentration can go to ppb level, parts per billion level. Then we are looking at such a small concentration of a target compound in a matrix. And then your system should be capable enough to identify those compounds at that trace level and give a 100% quantitative result. Your system should have the capability to do that. And these type of analysis are today known as residue analysis. Lot of analysis when we talk about even bioanalytical applications where you try to find out residual drugs in your biological fluid. It's a residue analysis. Forensic applications, forensic analysis. You are looking at extremely trace quantities of certain compounds in a biological fluid or in a different environmental system. These are all called trace analysis. Your system should be capable enough to do all this. That's a third requirement, high sensitive residue analysis. So these are the objectives of carrying out a GCMS analysis. Now there is something called 4S values. And this is basically for the students to understand. We talk about sensitivity. People may say my instrument is very sensitive, my detector is very sensitive, but what is sensitivity? Simple definition is change in the detector response whenever there is a change in the concentration of the target compound. Very simple definition, that is sensitivity. Talk about sensitivity, there are ways and there are different ways of finding out the sensitivity of a system. And we talk about signal to noise ratio and all those. I am not going into all those details, but sensitivity is a very common term. You are always exposed to this when somebody is coming to evaluate an equipment. They want to find out, we want to know what is the sensitivity of the system. So change in the detector response with change in the analyte, that is your target compound concentration. That is a very simple definition of sensitivity. Your system should be very sensitive, otherwise you will not be able to do residue analysis today. So it's a very, very important requirement of the system. Second one is selectivity. Selectivity means some people say the method is very selective. What does it mean? What is meant by selectivity? Relative freedom from interference. What is meant by relative freedom from interference? You consider a sample. Take for example, very simple sample. For example, I am trying to find out some residual pesticides in vegetable, maybe tomato or anything. I mean, so food product. Now, food product is a matrix laden sample. That means that sample contains lot of unwanted things also which can interfere in the determination of my target compound. What is our target compound? We are looking at trace pesticides. So when we are trying to do this trace pesticides by the technique, there are a lot of other compounds which can interfere. And all those unwanted compounds are commonly termed as matrices. And these matrices can interfere. And if they interfere in the determination of our target compound, then the authenticity of the result is no more. But then that means our results are not authentic. So that means we have to develop a method where there is absolute freedom from the interference. Nothing should interfere in the analysis of our target compound. Relative freedom from interference. That is what, when that happens, we can say our method is selective. Even if I am going to use that method, nothing will interfere and I am going to get an absolutely correct answer, relative interference. That is selectivity. The speed of analysis is very important, analysis time. Today's corporate world, that's a requirement. Suppose you imagine you have a sample and the sample is going to take 1 hour for the analysis by GC or GCMS. 1 hour, one sample takes exactly 1 hour or more. How many samples you can analyze in a day? 5 samples, at the most 6 samples, or at the most 7 samples, because you have to always take into consideration the heating and cooling time of your GC side also. So looking at all those, maximum 6 to 7 samples in a day you can, morning to evening you can analyze, because the sample is taking such a long time, 1 hour for analysis completion. That means if there are too many samples are coming into your lab, that is actually what is happening in today's world, today's corporate world, when so many samples, the sample load is very much, then that is going to be a problem. Because then if there is a way by which the total analysis time can be reduced, say from 1 hour to 15 minutes, that means the sample is taking 60 minutes to complete. The same sample in 15 minutes time, there is a 4-fold reduction. That means total time required by one sample per hour, we can analyze 4 samples. So what is the outcome? End of the day, if 7 samples or 6 samples, you will be able to analyze 20 samples or 30 samples per day. That means your output is going to be more 4-fold, 5-fold, and that is what is today's corporate requirement. Output needs to be maximized. So we are also the instrument manufacturer also aware of this requirement. We have fast analysis by DC and GCMS. We are trying to reduce analysis time and try to maximize. And last year is when you are buying an equipment, these are all costly capital expenditure. When you are investing so much of money in very advanced analytical equipment, it should give a total solution to your analytical problem. So these are 4 specificity, selectivity, speed of analysis, and solution. Okay. So we as so when we talk about GCMS, in particular, when you analyze a compound by GC, you are getting 2 information about the sample. It's a 2-dimensional information you are getting. One is you are getting retention time, and the second information is the detector response. Your XY graph, okay, retention time, gesture, detector response. So that is the 2 pieces of information you are getting in normal GC analysis. But when you analyze the sample by mass, other than this, you are getting one extra information. That means you are getting the retention time, second one is the intensity, and the third one which you are getting here is the mass. So, in addition to what you are getting, an additional information, the mass spectrum of a compound is also available in GCMS, and using the GCMS mass spectrum, we can identify the compound, even though we do not have the standards and is not required for qualitative validation. So please understand that the standards are not only quality quantification. But if you want quantification and it's required, please keep this in mind. Important point. Standards are required for quantification. Analytical chemistry, any type of quantification, whether it's GC or C or UV or thermic absorption, forms a quantification. You need to create a calibration curve. And for creating a calibration curve, you require standards. Same is applicable to GCMS or GCMS or LCMS also. So standards are required for quantification. But if you don't want quantification, you only want to identify qualitatively, then standards are not required. So this is a very important point to be kept in mind. Okay. So you get three pieces of information from a GCMS analysis output. You get retention time, you get the intensity, and also the mass spectrum of the compound. Okay, now what is the flow chart of a GCMS SQ? I have written SQ here. Please understand SQ means single quadrupole. We are only talking about single quadrupole mass spectrometer here. We have got a TQMS system also, that's called a triple quadrupole system, that's called GCMS, or what is popularly known as tandem mass spectrometer. We are not going into that. We are only remaining in our SQ discussion, that is single quadrupole. So this is a single flow chart of a single quadrupole system. Sir, everything is perfect. I am audible properly?
Yes, sir.
Okay. So flow chart of a GCMS system. Imagine you have a sample where different compounds have to be separated. So we are going to introduce the sample into GC. The sample has to go to GC first in normal case. You will find another arrow direct inlet. I will separately discuss about that. Okay. I mean, right now I have written, if you look at the slide, direct inlet. I will tell you what is that after some time, but right now I'm not talking about that. So you can see the sample is introduced into GC. GC contains a column. Column will separate all these compounds, and one by one, the sample compounds will come out of the column and it will enter the mass spectrometer. And the moment it enters the mass spectrometer, it is going to enter a place which is known as ion source. Three major parts of the mass spectrometer is one is the ion source, and one is the mass filter, and third one is the detector. And all the three, ion source, mass filter, and detector, they are all connected to a very powerful vacuum system, vacuum pump. That means the mass spectrometer is kept under a high degree of vacuum, which can go to 10 to the power of -5 to -6 torr. That's the level of vacuum we create inside the mass spectrometer. Whereas GC is open to atmospheric pressure, there is a carrier gas continuously flowing through the system. It's open to atmospheric pressure, but whereas it comes mass spectrometer, it is kept under vacuum. Okay, and there is an interface between GC and MS. That's called the interface between, because it's a hyphenated system. So the moment the sample comes, the compound is coming out of the column, it comes into the ion source, and that is the place where the sample is going to be ionized or fragmented. How it happens, we are going to see going forward. So once the sample is ionized in the ion source, we will be getting plenty of ions, plenty of fragments, depending upon the structure of the compound inside the ion source. And all these fragments, as I told you before, will be having various mass numbers. They are not same, they are all different. And they are all to be filtered, separated on the basis of their mass number, M/Z ratio. And that job is done by the mass filter. So the responsibility of the mass filter is to separate the fragments produced from the original molecule in the ion source. They're all separated by the mass filter, and all these fragments are taken to the detector in the shortest possible time. And the detector is going to give a signal, and that signal will be processed via that is your PC and software, and that is what you get as the mass spectrum. Okay, so this is the normal flow chart of a single quadrupole mass spectrometer, GCMS system. And so we are not talking about TQ system, only SQ system now. Now let us look at what are the ionization types that can be used in the GCMS. Because everyone knows, every student knows now the sample has to undergo ionization. That's a primary requirement. So there are two different methods, or rather I will say three. So the different methods, or broadly divided into two types. two different ionization methods in GCMS. One is known as very popular method, which is the default method, is called electron impact method, EI method. When you buy any GCMS system, any company, any manufacturer, the moment you buy a GCMS system, it will automatically come with this method of ionization, electron impact ionization, popularly known as EI method, electron impact ionization. Very, very hard ionization technique, very high energy electrons are involved, and the output is going to give you a lot of information about the molecular structure. Means structural information can be obtained from electron impact spectrum. Whatever mass spectrum you are going to create, whatever mass spectrum you are going to get with the help of a electron impact ionization technique, that will be very useful and it will provide you lot of information about the sample molecule. Then there is another ionization technique which is known as chemical ionization, or popularly known as CI method, CI. And in CI itself, there are two different types. One is a positive CI and one is a negative CI. Positive chemical ionization and negative chemical ionization. Well, chemical ionization is a soft ionization technique, whereas electron impact ionization is a very hard ionization technique. Okay, so in the case of electron impact ionization, the molecule will undergo near total fragmentation. It's a very, very hard ionization technique. The sample molecule will be almost 100% broken down. Near total fragmentation will take place. Whereas when it comes to chemical ionization, it's a very soft ionization technique. Low energy electrons are involved. Too much of fragmentation of the sample will not take place, and it will give a positive chemical ionization, will give information about the molecular weight of the sample. So it is one of the most elegant way of finding out the molecular weight of a compound. So you can get molecular information from PCI, positive chemical ionization. Many times when you go to pharmaceutical companies and all, they try to use EI and EI as complementary to each other. They must, but please understand, electron impact ionization will automatically come as a by default method when you buy a GCMS. But CI will not come by default. You have to separately purchase it. It is not by default. If you want, you have to specially purchase that CI mode. And there's a cost involved. So but if you don't want that, you don't buy. You only use CI, will automatically come in the instrument. Okay. Now we have negative chemical ionization, NCI, and especially for analysis of very, very trace quantities of electrophilic compounds. And students understand what is electrophilic compounds. Mean any sample, any compound which has got affinity for electrons, which can absorb electrons, they are electrophilic compounds. For example, the very, very fine example is any halogenated samples. They are highly electrophilic compounds. And there are a lot of applications in food safety also. There are a lot of chlorinated pesticides in the food products, and they are all present in extremely low concentration. We can use an NCI mode for the qualitative and quantitative analysis, negative chemical ionization mode, because they are all highly electrophilic compounds. So we have, in total, we have three different modes of ionization in GCMS. One is electron impact ionization, a default method in the equipment. Hard ionization technology, you get lot of information about the sample molecule. Then we have positive chemical ionization, which gives molecular weight information of the compound. We have negative chemical ionization mode, which is very useful for trace analysis of electrophilic compounds in the sample. So these are the popular ionization modes available in the case of GCMS. How electron impact ionization takes place? So when the sample is coming to the ion source, that's the first part, the ion source. When the sample is coming to the column, it will enter the ion source. So what you see here is the ion. See, in the ion source, there are two filaments. One is a filament at the top, and the filament at the bottom. The filament at the top, basically this filament is heated, electrically heated. And at a certain temperature, high temperature, this filament, the filament at the top will start emitting thermal electrons. And these thermal electrons have got a very huge quantum of energy, 70 electron volt energy. And this filament will be emitting those thermal electrons. And the filament at the bottom is a collector. It's actually pulling this down, pulling all these electrons down. That means it is accelerating, actually pulling it down. So one is the filament at the top is the emitter, and the filament at the bottom is the collector. So there is always a flow of electrons from top to bottom. And when my molecule, you see this red, what you see here is the red, this is the sample molecule is coming from the column. When it is passing through the ion source, all these electrons will come and bombard the sample molecule. And the bombardment is taking place with such a huge quantum of energy, because most of the organic compounds will be having an ionization potential somewhere around 15 to 20 eV. And these electrons are having almost 3 to 4 times more energy, 70 electron volt. It's a huge impact of this bombardment. The sample molecule will be simply fragmented, it will be broken down into pieces. And then you get lot of fragments coming from the original molecule in the ion source. Now these fragments have to be removed at the quickest possible time. Otherwise, within very short possible time, another compound will come from the column. So before the second compound comes, all the fragments produced from the first compound should be removed. Otherwise, there will be mix-up. That should not happen. So all these fragments are going to be separated by the mass analyzer. And how it is going to happen, we are going to see. And then the ion source becomes empty. Then another compound will come from the column, and the same process gets repeated. And so whatever fragments are formed in the ion source, they are all taken by, they are all separated by, they are all filtered by the mass analyzer. They are all sent to the detector. Detector is going to give an output, which is the mass spectrum. What you see below is the mass spectrum of methyl stearate, methyl esteric acid. And if you look at the x-axis, is all mass number, atomic mass number. And what is on the y-axis, it is the relative intensity or relative abundance of the ions produced. And if you look at the mass spectrum very carefully, you will see that it's a very complex mass spectrum that is going to be produced by the EI mode. Because now we know EI mode is a very harsh ionization, very hard ionization technique, and the molecule undergoes near total fragmentation, because almost totally it is fragmented. Okay, so you get various, so the students, you can see each line here, each line in the mass spectrum represents one fragment. For example, there is a line at 74, that's a fragment which is having mass number 74, and that has got the maximum intensity. That means the fragment with mass number 74 is formed in maximum proportion. And all other, the intensity of all other ions are calculated with respect to mass number 74 ion, considering it as 100%. We assume the 74 as 100%. It's a theoretical assumption. And considering 74 fragment as 100%, we try to calculate what is the ratio, what is the intensity of 87 fragment, what is the intensity of 143 fragment, like that. And this is called the intensity ratios of various fragments. So the one which is formed in maximum proportion is assigned a value of 100% intensity. It's a theoretical assumption. And based on that, the intensities of all the fragments are calculated. And then you look at the mass spectrum, which is produced by EI. The most intense peak is called the base peak. Please understand, this is a very important point when you try to go for identification of the compound by mass library. Because we have got a mass spectral library available, and how the mass spectral library is going to work is based on, it tries to identify what is the base peak in the mass spectrum. So the base peak is nothing but the most intense peak that is appearing in the EI spectrum. So this is a EI spectrum of methyl stearate, and is produced by electron impact ionization, and it is going to be a fingerprint of the compound. Now we are going to positive chemical ionization. Positive chemical ionization, I told you, is a very soft ionization technique. Too much of fragmentation will not take place. Here we require a reagent gas here. In the case of normal GCMS, we require only one carrier gas, that is helium. Yesterday we spoke about GC, where we are using predominantly nitrogen as the carrier gas. But in the case of GCMS, we use only ultra pure helium as the carrier gas. No other gas is required. In the case of FID, we require hydrogen, we require air, we require makeup gas. No, those type of gases are required. Only one carrier gas is required, that is helium in the case of GCMS. When we have a positive chemical ionization technique, we require a reagent gas also for this mechanism to take place. Okay. And what are the reagent gases that are normally utilized? Methane, number one. Number two is iso or high purity. Methane, number one. Isobutane, number two. And ammonia is number three. So these are the three reagent gases we normally use, out of which the most common one is methane. Methane is the one which is most widely used reagent gas in PCI, positive chemical ionization, as well as in negative chemical ionization. But why this reagent gas is required? What we do, before we introduce the sample into the GCMS system, we try to introduce a very small quantity of the reagent gas. And all this can be controlled through the software. The valve will open, the gas will get in. All those, these are all software operations, nothing like manual operations. Okay, a small quantity of the reagent gas is introduced in the ion source. And ion source, what everyone knows, ion source electrons are there, high energy electrons are there. And these high energy electrons will go and bombard with the reagent gas. Say, for example, methane. And methane will undergo fragmentation. Ion molecular reactions will take place. And some stable reagent ions will be produced. And then when we introduce our sample, that is considered our sample is M, our molecule is M. When it goes inside, there are plenty of stable reagent ions, and these reagent ions will collide with the sample molecules. So that's a secondary collision. Okay. And so the next slide will make it very clear. So reagent gas reacts with electrons to form reactive species. Result is very soft ionization technique, which results in primary formation of molecular ions. And from the molecular ion, we can actually understand what the molecular weight of the compound. So main use of CI is molecular weight confirmation. So many times, as I told you, in pharma industry and all, they use EI and CI as complementary technique. They analyze the sample by EI mode, get the fragmentation pattern, and then analyze the sample again under CI mode, get a confirmation about the molecular weight. It becomes a foolproof identification of the compound. So a positive chemical ionization, this is what happens. Two steps are there. First of all, when the reagent gas goes inside, the electrons will bombard the reagent gas, and these reagent gas are going to create some stable ions like when we are using methane as the reagent gas, we get some stable reagent ions like C2H5 plus and CH5 plus. And then there will be a secondary collision between these stable reagent ions and the molecule. And when the CH5 plus is colliding with the molecule, one proton is transferred from the reagent ion to our molecule, and CH5 plus will go back to a very stable form CH4, and our molecule will get an additional proton M plus 1 or M plus H. Okay, so that is actually what happens. So what you see here, the same methyl stearate spectrum is shown here, which is analyzed under CA mode. You had seen the spectrum of methyl stearate under EA mode. You have seen lot of fragments coming in. Here, if you look at this spectrum, it's a very, very simple spectrum. You don't find many fragments here. And if you look at towards the right-hand side of the spectrum, you see there is a very strong fragment coming at mass number 299. That's nothing but an M plus 1 peak. Because methyl stearate molecular weight is 298. So when it was analyzed by CA mode, and because of this positive chemical ionization reaction, one proton was supplied by the reagent ion to the molecule. That means the methyl stearate molecule has received an extra proton, thereby the molecular weight going up by 1 unit, 298 plus 1, it has become 299. So the strongest peak here is 299. So that is an M plus 1 peak, and M plus 1 minus 1 is 298 is the molecular weight of the compound. So here there's just understanding for the students. The first electron ionization, so we are using methane as the reagent gas, CH4. And when it is when the collision takes place between methane and the electron, CH4, it is CH4 plus 2 electrons, and other fragments like CH3 plus and CH2 plus, they also can form. And the secondary collision, ion molecular reactions create stable reagent ions. Example, CH4 plus can react against CH4, it gives CH3 plus CH5 plus. Similarly, CH3 plus CH4 can C2H5 plus. So when you use methane as the reagent gas, the most prominent ions are CH5 plus and C2H5 plus. They are formed in maximum proportion. And these will collide with the sample molecule with a reduced energy, somewhere around 15 to 20 electron volt energy. And thereby the extra proton from the reagent ions will be transferred to the molecule. It is essentially a protonation reaction that is taking place. Sample becomes M becomes Em plus H. Okay. Now this is a comparison of mass spectra. Some sample we have analyzed by the what you see, the two different mass spectra. The first one is EA mode and second one is PCA mode. So if you compare the what you call the complexity of these two spectra, you will see it's very simple for you to see that the first one, EA mode spectrum, is very, very complex, too much of fragmentation, very complex mass spectrum, but it gives more information about the sample structure. Look at the spectrum which is on the downside spectrum, that is created by PCA mode, and very simple, not many fragments are seen, but you will find a very, very strong fragment at the end that represents the M plus 1p. So from one spectrum, you are getting structural information, and from the PCA spectrum, we are getting molecular weight information. So that is why today GCMS has become a very powerful analytical technique for the analysis of unknown compounds. Okay, then we go for one step ahead when we talk about GCMS, MS and all, not in this session. And there are a lot of advantages even over this GCMS. When we talk about MS, it has got much more advantage or even a single quadruple MS. I mean, this is not the forum for that discussion. Okay. Now, similarly, negative chemical ionization, I mean, the same reagent, same system is the same technique is taking place. Only thing, we are actually collecting the negative ions formed because the sample molecule is absorbing low energy electrons to form a negative radical or negative ion. And those are collected by changing the polarity in the system to the softer. So in the case of CI or EI, we are only collecting the positive ions, whereas in the case of NCI, we are collecting the negative ions. There is a polarity switching which actually happens to the software. And this is an excellent technique for the analysis of trace analysis of electrophilic compounds. Any sample which has got an affinity for electron, any sample which has got the capacity to absorb an electron and form a negative radical. And this is a wonderful technique. Same thing in case of GC, we have a technique. If you remember yesterday, I told you electron capture detector. That also is doing the same job. Electrophilic compound determination to very low levels of detection. But electron capture detector is a wonderful detector. It's a wonderful detector for GC, but you have to be extremely cautious because there is a radioactive isotope inside. You require a permission from BARC to install the detector in your GC system, and lot of precautions have to be taken because of the radioactive material inside the detector. But when it comes to ECI, NCI, and GCMS, those hassles are not there. But only thing, NCI is going to be price-wise, it is going to be slightly more. So that's only. So negative chemical ionization technique is to be used only in case you want to detect some electrophilic compounds in trace analysis. Otherwise, it is not required. When you are coming to the second part, now our ion source is over. We are coming to the second part, mass analyzer. Mass analyzer, what is the responsibility of the mass analyzer? Now we know when the sample undergoes fragmentation, many fragments are going to be produced inside the ion source. Each fragment is having a different mass number. So it's a mixture. What I told you, the example before, when a glass bottle is falling down, produces lot of fragments having different weights, the same way. the sample molecule is getting fragmented, produces different fragments, different ions having various mass numbers. And have to be separated. Who will do that? Mass analyzer. Mass analyzer, or sometimes it is also referred to as mass filter. Both are same. So it is an integral part of the mass spectrometer system, which is responsible for the separation of the ions or the fragments produced from the original molecule in the ion source. And this separation is done on the basis of their mass number. So they are all separated on the basis of mass number, and all these fragments are to be transported to the detector so that the detector will give the final output, which is the mass spectrum. Now, what are the mass filters available? There are different types of mass filters available. Like one is double focusing magnetic sector. Very, very expensive, not very common. In industry also, you may not find normally a double focusing magnetic sector mass spectrometer. It gives a very, very high resolution, but that is not required in industrial applications. Used maybe in some research laboratories or universities where people are doing a lot of basic research. People are interested in very, very, very high resolution than magnetic sector, because the cost of system is very, very high. It's extremely high cost of the system. So that is why the industry normally not utilized in magnetic sector. Quadrupole is the one which is most widely used in industry, quadrupole system. And it is a benchtop system, quadrupole system. Then we have, and so what we are going to discuss is quadrupole, because most of the mass spectrometers available today, most of them are utilizing a quadrupole system. So we will discuss about quadrupole. Time of flight, high mass range. For example, you talk about, for one real example is protein analysis, proteins and peptides, or high molecular weight compounds, biomolecules. So large molecules where the molecular weight can be like more than 3,000, 4,000, 5,000 Dalton and all. We normally use a mass filter which is time of flight. But we are using a time of flight mass filter. Our ionization technique is different. It is MALDI. Most of you must have heard about MALDI-TOF systems, matrix assisted laser desorption ionization time of flight. It's a MALDI-TOF system. But that is basically for very high molecular weight compounds. Then there is another one benchtop is also ion trap. Ion trap works on a different principle, but sometimes nowadays people prefer more of a quadrupole system because of its inherent advantages. So there are different types of mass filters available. So it's a very simple, very single stage quadrupole MS. Very simple to use. Okay. On the extreme left hand side, what you see is the ion source. Your sample has undergone fragmentation. Many different fragments are produced. Each one is having its own mass number. Now they are all separated by what you see here. The center is the quadrupole system. You will see a much better slide, the next one. And then at the last one, what you see is the detector system. All these fragments from the ion source are filtered, separated, and sent to the detector by the quadrupole mass analyzer. Ion source becomes empty. Next compound will come. That will also undergo ionization, and the process will continue. So this is how a mass spectrometer works. So now this is a typical quadrupole. So quadrupole, the name itself says there are four rods. That's why it's known as quadrupoles. 4 rods, cylindrical rods, and they are kept one at the top, one at the bottom, and 2 sideways. Okay, 1 rod at the top, 1 rod at the bottom, 1 on the left hand side, 1 on the right hand side. Okay, so 2 at the side. So 4 rods is an arrangement. So that's called a quadrupole. There are 4 rods, and the pairs are connected. Okay, the one pair, maybe the top and bottom, one pair is connected. We are applying a DC voltage, and another pair we are applying a radio frequency RF. So there is at any point of time there is a ratio of DC to RF. Okay, so for a certain ratio, now only one fragment from the ion source having a certain mass number can travel through the space between the rods without touching them. You can see the green line So that represents one particular fragment, and it is passing through the space. It will not touch any of the rod. If it touches, then it will get deactivated. So it should not touch. It is not touching because at this particular ratio of DC to RF, one particular fragment has got a very stable trajectory. It will be passing through the space between the rods and it will go to the detector. So that means we are successfully able to extract one particular fragment from the ion source and taken to the detector. But our intention is always to take all the fragments, not only one fragment. So for that, what we do, we continuously change this ratio, and for every ratio, one fragment will come out and go to detector. And the shortest possible time, all the fragments will travel through the space between the rods and they will go to the detector, and the detector is going to give a output which is a mass spectrum. So ions are scanned by varying the DC to RF voltage across the quartz, and that is how we are filtering all these ions. That is how we are separating all these ions based on their mass number. So now all the fragments produced by ion source are taken to the detector. Detector is nothing but an EMT. It's called an electron multiplier tube. And that gives an output. That output is the mass spectrum of the compound, which is the fingerprint of the compound, as I told you before. Capabilities of a quadrupole system: it can carry out excellent qualitative analysis for multi-component system. Please understand, that's why quadrupole is very popular today. It can carry out excellent qualitative analysis. And the most important capability of a quadrupole system is the second point: can provide very, very reliable library search results. See, everyone knows today we are not going to inject any standard for the identification, qualitative identification GCMS, because in the system, we have a mass spectral library. When you are purchasing the instrument, you can get it along with a mass spectral library will be provided. It contains more than 3 lakhs of mass spectra. And once your sample is analyzed and it produces a mass spectrum, the software, there is a search engine, the software will always search this mass spectrum against all those lakhs of mass spectra which are present in the library, and the shortest possible time you will get a perfect match. That is how we try to identify without any standard. So this system, a quadrupole system, can provide very, very reliable library search results. That's one of the most important capability of a quadrupole system. And it has also got very good quantification capability and very easy to use. And that's why today, if you look at, you go to any other industry, you look at any other GCMS or even MSMS, many times you'll say many people are using a quadrupole system. This is how the quadrupole system looks like. And there are 4 rods. You can see only 2 and 2 are on the other side. And it's a very, 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 so we have, this is just a, what you call the hardware. You can just forget about it. Okay. Now, how to improve the sensitivity? Even we spoke about forest values. The number one was sensitivity. And I gave you that simple definition also, sensitivity. Today, everyone speaks about sensitivity. Somebody wants to buy a GCMS, somebody wants to buy a FTIR, or somebody wants to buy any other equipment, and they want to find out why, they want to know what the sensitivity system, because I want to buy the best equipment. I want to buy the equipment which has the most maximum sensitivity. So sensitivity, any electronic equipment, the sensitivity is always defined in terms of signal to noise ratio. Signal and noise. It is very difficult to design an electronic equipment without noise. Means any electrical disturbance, disturbance because of electronics, disturbance because of any other lot of parameters which can produce baseline disturbance. These are called noise in our technical term. We call it as noise disturbance. And the manufacturer also takes so much of care to produce an equipment where the noise level is at the bare minimum. Noise should be minimum and the signal that is going to come from the sample should be maximum. Then there is a ratio called signal to noise ratio, S by N ratio, which can be proved with the help of authentic standards when we are evaluating a system. More the value for signal to noise ratio, more sensitivity for the equipment. And in a quadruple system, we can use a method called SIM method, which we are going to see to increase the signal. We can increase the sample signal by adopting a method called SIM method in GCMS analysis. And if you are using an ion trap system, you can use an MSMS mode to reduce the noise. But whether you increase the signal or whether you reduce the noise, the ultimate effect is going to be a better signal to noise ratio. That means an improved sensitivity of the system. Okay. Now the analysis modes in GCMS, there are two different modes of analysis. One is known as a scan mode and one is known as SIM mode. Scan mode is used normally for qualitative analysis, and SIM mode is used only for quantitative analysis. And I told you one point to be kept in mind. If you want to do quantification, you should have standards. Without standards, you cannot do quantitative analysis in analytical chemistry. Applicable to any technique, whether it is UV, FTR, or GC, or MS, or LCMS. Standards are required. But qualitative analysis in the case of GCMS, standards are not required. So scan mode is used for the qualitative analysis, that is only for identification, and SIM mode is used for quantifying the target compound. So we'll see what are those. Scan mode of operation, scan mode of analysis. Scan mode is used for quantitative analysis. Scanning is performed continuously at a regular interval from a lower mass number to a higher mass number. So when you are going to use your GCMS for the analyzing a sample using scan mode, you have to set a value, one range. From so-and-so atomic mass number, I am going to so-and-so atomic mass number. That you have to set. Lower end, higher end. Normally we prefer, say, normal operations, we start from, say, 40 AMU, 40 mass number. Then we go to 400 mass number or 500 mass number as per the requirement. But normally we start from 40 mass number. So that is the lower range and upper range. So you need to set this lower range and upper range of your mass number scale in the software before starting the analysis. And once the analysis is when the sample is getting analyzed and when fragments are produced, the system is going to scan all the fragments produced between these two ranges, lower range and upper range. How many fragments are produced? All the fragments will be seen by the detector. Detector is going to look at each and every fragment produced between the lower range and upper range of the mass number. And this gives a lot of qualitative information. Okay, so the mass spectrum produced in this manner by the scan mode is utilized for structural information and library research. So please keep a very important point in mind. You have to use a scan mode of operation if you want to go for library research. Never ever do library research by SIM mode. You'll get wrong result. SIM mode is used only for quantification, not for library research, not for qualitative analysis. If you want to do qualitative analysis and perform a library search to identify the compound, do only scan mode of operation. SIM mode is purely for quantitative analysis. Okay. Now let's see what is SIM mode. SIM stands for Selected Ion Monitoring Mode. Selected Ion Monitoring Mode. That is the full form of SIM mode of analysis. So SIM stands for Selected Ion Monitoring, used for only quantitative analysis. Now imagine your sample is fragmented in your ion source. Suppose your sample is going to give you, the sample molecule is going to provide you 20 fragments or 25 fragments. And in normal scan mode, the detector would like to see all those 25 fragments because it wants qualitative information. But when it comes to SIM mode, I am not interested in all those 25 fragments. I am going to do a quantitative analysis for which I am going to select 4 or 5 most prominent fragments in the mass spectrum. I don't want all the 25 to be seen. I am going to select That's why it is known as selected ion. You are going to select. You are going to select maybe 3 or 4 or 5 prominent, intense fragments you are going to select. And then you are going to feed these fragments in the software. And what the software will do, what we will see in the next one. So used only for quantitative analysis. In this mode, only the selected ions or the sample molecule will be monitored by the detector. So detector will be able to see only those selected fragments which you have selected. Other fragments are not seen by the detector, not be visible. That is why you should not go for a qualitative identification by library search by this mode. You will get a totally erroneous result. Because here the detector is only looking at the fragments which are selected, maybe 3 or 4 or 5 maximum, that's all. Even though you can select more, but normally we select only 3 or 4 or 5. So only those fragments will be seen by the detector, but it gives a very, very sensitive quantitative analysis. So that is the utility of your SIM mode, quantitative estimation. Okay. For example, we have analyzed a sample. The sample had given multiple fragments, but we have selected only 3 fragments which are very prominent. Fragment at 54 mass number, 72 mass number, and 152 mass number. So when we are feeding these 3 fragments in the software, it is creating 3 compartments. You can see one compartment, there is 54, second compartment 72, and the third compartment 152. So in the first compartment, the DC to RF voltage ratio is kept only for the detection of 54. In that particular ratio, only 54 will be seen, nothing else will be seen. And the second compartment, we are going to keep a ratio DC to RF ratio, which is suitable for 72. So there only 72 will be seen, nothing else will be seen. And similarly, in the last compartment, the system will keep a ratio, a DC to RF ratio, which is suitable for only 152. So 3 different compartments, because we have selected 3 fragments, 3 different ratios, DC RF ratios are also fixed. For when other fragments are coming, they don't have any suitable ratio of DC to RF, so they will be totally invisible. So system will be able to see only these 3 fragments, and then based on these 3 fragments, you can get a absolutely good quantitative result. So it is an excellent quantitative analysis. Okay. Sometimes people use a SIM mode of operation even to get rid of unwanted matrix also. Even though it is not a 100% way of removing matrix, a more effective way of removing matrix. Matrix means any unwanted sample from the which may interfere the target. They are called the matrix. A more suitable matrix removal system is your tandem mass, MSMS. But sometimes we can even use a SIM mode for removal of interfering compound. By carefully selecting the fragments which are coming from the sample molecule, we can get rid of the matrix or unwanted things so that we can clearly see the target compound by the use of SIM mode. Even though it is not as effective as using a MSMS system. MSMS system, it is a much more useful way of removal of matrix by using a tandem mass spectrometry. So, that's a different technique we are not discussing, but sometimes even using a SIM mode of operation also we can get rid of to a certain extent unwanted interfering compound that is called matrices. Why vacuum is important in mass spectrometer? Because we are creating vacuum. When we start the GCMS system, when we come to the lab in the morning, normally for your information, GCMS is never switched off. When we are leaving the lab in the evening, we never switch off the equipment. We never break the vacuum. It is 24 hours it is on. Any vacuum system, it is always better to keep it 24/7. Unless there is a requirement for a servicing problem, unless for replacing some parts or something, you can break the vacuum, you can shut down the system. Otherwise, it is always desirable to keep the system on 24 hours. We have a lab, in our lab in Mumbai, Shimatsu lab, we have so many MS systems, we never switch off the systems. It will be running 24 hours, continuously it is running. And at the end of the day, when we leave the lab, we reduce the temperature of the column, we reduce the temperature of the injector, but the vacuum is never broken. The instrument is never switched off. So that's the ideal situation. But when we go to different customers, many times, especially these government customers, they don't prefer to, they may be having their own rules and regulations. They try to switch off the system maybe at 5 o'clock or 6, whenever they are leaving the lab. And again, next day they are coming in the morning and again switching it on. You are going to waste a lot of time. Okay. So why this vacuum is important? Why the vacuum should be maintained? It's a very, very important point. Vacuum is applied to pump out the residual gases like air and water vapor. See, if you are switching on the system, any vacuum system, when you switch off, atmospheric air will go inside. Atmospheric air contains water vapor, nitrogen, oxygen, all those. Okay. And suppose tomorrow when you are coming and starting the system, and these gases are going to remain there. Nitrogen is going to remain there, oxygen is going to remain there, water vapor is going to remain there. And when your sample undergoes fragmentation, there is a possibility that your sample fragments will collide with these gases. They will collide with nitrogen, collide with water vapor, collide with oxygen. Lot of collision will take place. These are called residual gases in the system. They will collide with your sample fragment, and that will produce lot of disturbance in the basin. That's called noise level production, thereby drastically reducing the sensitivity of analysis. And we don't want this to happen. That is why all these residual gases should be pumped out. We have to remove it. We have to pump it out. That's the reason why we are applying vacuum. So vacuum is applied to pump out the residual gases like air and water vapor. This prevents the chances of collision of the ions produced from the sample molecule and the residual gases. And if these type of collisions take place, it will produce very, very high background, reducing the sensitivity. So good vacuum reduces noise level and improves sensitivity. So to get a better sensitivity, vacuum is also one of the factors to be kept in mind. It's also a very, very important factor. Unless the vacuum is proper, unless the vacuum is good, we normally don't start the analysis. We should get a very good and very clean vacuum before we start our sample analysis. This is just for students to understand main components of GCMS. So we have the right hand, so we have say GC on the right hand side, on the left hand side you see the mass spectrometer. So there is an injection port, there's a capillary column inside, and there is a heated interface. You can see that's a connection, that's a bridge between the GC and the mass spectrometer. And then the first part you see is the ion source. The sample compound will come here, it will undergo ionization. And then what you see here is the white rod, that is the mass analyzer, that's a quadrupole. And the extreme backside, that white part you see, that's a detector. And here what you see is the blue, that's a turbomolecular pump. That's a very powerful vacuum pump which is inside the system. And that is what is creating the final vacuum inside the mass spectrometer, which can go to the level of 10 to the power of -5 to -6 torr. Okay. Variable ionization voltage also, I am just going through some of this, software parts I am skipping because the time may not permit me to go into details. 70 electron volt energy is by default. In the ion source, when the electrons are coming and bombarding the the sample molecule, these electrons are having 70 electron volt by default. And that's why it's a very, very high energy collision process. But there is a system, there is a possibility through software, you can even change the ionization voltage. From 70, I can change it, I can make it 50, I can make it 40, I can change it if you want. By changing, why you want to change? Suppose in sometimes even by changing the ionization voltage, you will be able to see a molecular ion. That means sometimes you can get some information about the molecular weight, because a molecular ion formation will become enhanced when you go for a lower ionization voltage. So that's a facility given in the software for the user. Okay. I mean, this is I'm skipping this. Now, yesterday I told you about retention index also. Is a much better way to identify a compound, retention index. And what is the difference between retention time and retention index? Retention time is always condition dependent. It depends on analytical conditions. If your analytical conditions are changed, retention time of a compound can change. But retention index of a given compound, of a chemical compound, on a given stationary phase will be always a constant irrespective of the conditions. That's the biggest advantage of retention index. So retention index is not depending on conditions, whereas retention time is depending on that. So this is a way of identifying the compound based on and what is retention index. So if you want to find out the retention index, of course this is software operation. I'm not going into those details. Retention index, if you want to find out in GCMS, you should have a standards of N alkanes, normal N alkanes, and starting from C7 to say C33 N alkane mixture is provided to you, and there are certain conditions and column prescribed, and you have to inject the sample, and all these N alkanes, paraffins, N paraffins, they will get separated. And you can see here on the screen like C20, 21, 22, 20 there, you can get a very good, wonderful separation. And by definition, by convention, the retention index of a saturated hydrocarbon is the carbon number multiplied by 100. So that means for C20, the retention index is 2000, 21, C21, it is 2100, 22, 2200 and so on. So first we get a separation of the hydrocarbons, then we inject a sample. Now you can see your sample component is coming between C21 and C22. It is eluting between the retention times of 21 and 22. Okay. Now we know C21 is having a retention index of 2100 and 22 is having a retention of 2200 and our compound is coming in between. That means logically, you know, the retention index should be between 2100 and 2200. This will be automatically calculated by the software. What the software does, the distance between C21 and C22 is divided into 100 equal parts. And then it will look at on which part our sample compound is coming. Our sample compound, you can see it is coming on the 42nd division. So the retention index of this compound is 2100 plus 42. It becomes 2142 is the retention index of this compound. On this given stationary phase, it will never change. Whatever you change the analytical conditions, you change the temperature, you change the flow rate, you change the pressure, this 2142 of this compound on this column will not change. If you change the stationary phase, if you try to use a different stationary phase, different column, then it can change. Otherwise, it will not change. So it is a wonderful way of identifying the compound based on retention index. It's a total software operations. I am not going into those details because time will not permit me because we need to see some important applications also. And I told you about time, speed of the 4 S values. The third S value was speed of analysis. I told you how to reduce the time of analysis so that it can increase the output. There is a mode known as fast GCMS mode. We can reduce the total analysis time. And if you want to carry out a fast mode of analysis, there are certain requirements for the hardware. Your GC oven, column oven should have a very, very high heating rate. It have a very high head pressure. You should be able to apply a very high pressure while we introduce the sample, inject the sample into the system. Then we should have a very high split ratio because here we are going to use a microbore capillary column. If you remember what I told you yesterday, there is a column having internal diameter of 0.1 mm, which is called a microbore capillary column. And that is the column we are going to use in the fast mode of operation. What you can imagine 0.1 millimeter internal diameter of the column. Such a small ID column, you need a very high pressure for the sample to go in. So you have a very high, and again the sample quantity that can be sent to the column is also extremely small. So your high split ratio is required. And the mass spectrometer also should have a very high scanning rate. These are some of the requirements for carrying out a fast analysis. And our system, what we are offering is having all those requirements by default. Just to give an example, this is a perfumery compound. We have analyzed by normal GCMS. I have shown you two different chromatograms here, ion chromatograms here. One is normal GCMS. The sample has taken approximately 50 minutes. Consider it as approximately 1 hour. The same sample is analyzed under fast mode, and then you can see the analysis getting completed in hardly 7 minutes or less than 10 minutes. So that means the sample which is taking 50 minutes or more than 50 minutes is getting analyzed in hardly 7 to 8 minutes time. It has become 4 to 5 times faster. That means in 50 minutes time, I can analyze at least 3-4 samples. That means my output is going to be more. That is the order of the day. That's a requirement of the day, especially in the corporate world. How to maximize your output? Because the workload is going to be more. Like you in a very busy lab, your output should be very high. We are not compromising on the resolution also. Resolution is going to be same, but we are only reducing the total time. There is a 4-fold, 5-fold reduction in the analysis time. And this is the direct inlet probe. I told you when I was showing the block diagram, I told you I will talk about this later. If you have a very pure compound, especially this is applicable in pharmaceutical industry. If you have got a pure dry, very pure compound, very pure pharmaceutical drug, no impurity, nothing to be separated. Even if you go to inject into GC column, you will get a single peak because it's a highly purified sample. But if you inject into column, you have to wait for the sample to come out. But instead of that, wasting so much of time, you can directly put the sample into the mass spectrometer with the help of this probe. This is known as a direct inlet probe. A very fine, small, very small quantity of sample can be kept inside this probe, and this probe can be pushed into the mass spectrometer, and hardly 4 to 5 minutes time or 5 to 6 minutes time, you will get the complete information of the sample. But only thing, this is applicable for pure compounds. It's a highly complex sample. You cannot use it because mass spectrometer, as you know, it has no separation capability. So this has been pure compound. So this probe is normally utilized, maximum utilized in pharmaceutical industry because they are working with very pure drugs. Okay, this is a DAMS analysis. This is a drug, and we have carried out a DAMS analysis, not a GCMS analysis, DAMS analysis. And molecular weight, look at the molecular weight, it's more than 600. Normal case, we may require a derivative session if it is to be separated by GC. But here nothing is required. You can directly send the sample into mass spectrometer. You can get a mass spectrum. You can go for a library search. And all this you are doing in hardly less than 10 minutes time. Now that's the biggest advantage. Okay. We are coming to the last part of this discussion. Important applications of GCMS. Pharmaceutical industry, pesticides, perfumery, food industry, petroleum, polymer industry, environment, biomedical applications, forensic applications, spices, essential oils, textile industry, ROS applications, biofuels, biotechnology. There's a long list of areas where you can use GCMS. In pharmaceutical applications, yesterday also I told you one of the important applications, residual solvents in API. Residual solvents, as per, suppose we are doing it as per USP. If you look at USP monogram, USP method number 467, you have to find out what are the residual solvents in pharmaceutical drugs by a GC or GCMS in combination with a headspace sampler. You require an attachment also, headspace sampler. Then you can identify intermediates in API manufacturing, impurity profiling of API, analysis of raw materials, molecular weight of pure drugs. These are some of the important applications we can carry. This is just for the students to understand what is meant by headspace injection. Analysis of volatile fragments in a non-volatile sample. Your sample is non-volatile, but it may contain some volatile fragments. You take a small quantity of sample in a vial, so normally standard vial is always 22 ml vial. Take the sample and then you can actually seal it. There is an aluminum cap and rubber septum you are sealing, and then you start heating this vial in the instrument. In the instrument means the headspace attachment. This attachment is connected to GC. So there is a small oven available in this attachment. You have to keep this vial and start heating, and then it will undergo equilibration. That means the volatile fragments will come out of the sample, but it cannot escape because your bottle is totally sealed. So these vapors will accumulate inside the bottle. Then after some time, a syringe will go inside and collect a certain quantity of vapor, whatever you have specified, without touching the sample, and then it will come out and automatically go and inject into the GC. That means we have introduced only the pure vapor of the volatile components in the GC. That means your GC column will not get contaminated, your detector port will not get contaminated. Lot of advantages, lot of sensitivity. So there are two different types of headspace mechanism. I will not be going into those details. One is called the syringe mechanism. That is what I have shown you. And there is another mechanism which is known as transfer line mechanism. Instead of using a syringe, you can transfer a small quantity of the vapor from the bottle to the column directly through a transfer line. So we have a instrument for that, HS20. We are providing that, and that uses a transfer line mechanism. And whatever you have seen before is a syringe mechanism. Both systems are available with us, and that's basically for headspace analysis. This is a typical example of residual solvents in a drug. As per USP method, class 1 solvents. These are the 5 solvents specified in USP, United States Pharmacopoeia. 1,1-dichloroethene, 1,1,1-trichloroethane, carbon tetrachloride, benzene, and 1,2-dichloroethane. You can get a very clean separation. We have used a RXI 625 SIL MS column. It's a medium polar column. It's a cyanopropyl modified dimethyl polysiloxane column, 30-meter length, and the film thickness of the stationary phase is 1.8 micrometer, and the diameter is 0.32 mm internal diameter. So that's the column what we have used. And you are seeing this is a residual solvents in a pharmaceutical drug as per USP method. Then this is CA drug of the molecular weight of a spectrum, molecular weight of a drug, and carried out by GCMS in the CA mode. And looking at the CA spectrum, you can easily find out what is the molecular weight of the compound, because we are getting a M+1 peak at 208. That simply tells you the molecular weight is 207. This is a DAMS analysis of steroids. One is prednisolone. Normally, steroids can be analyzed by GC, but after derivation, we have to prepare a TMS derivative, trimethyl-silyl etherification reaction. We have to carry out with DSTFA reagent in pyridine medium, convert the steroid to TMS derivative, and then inject into the column. Otherwise, no. But here, I am not doing all those. We are directly introducing the steroid into the MS system using a probe. So now it is a DAMS analysis, not a GCMS analysis. That's the utility of your DAPO, but it's a pure compound. So even difficult samples, high molecular weight compounds, even non-volatile samples can be analyzed with the help of a DAPO. And these are some of the herbal drugs. Herbal drugs are extremely polar, very difficult to analyze by column normally. You have to do a lot of sample preparations, a lot of derivatization, but with the help of DAMS, we can achieve a separation, we can achieve the analysis, and we can even go for a library search and identify the compounds. Very simple. And genotoxic impurity, especially for pharmacy students, they must be knowing about this. A lot of genotoxic impurities, especially during the API manufacturing, and many of them are genotoxic, many of them are carcinogenic, like methane sulfonic acid ester, benzene sulfonic acid ester, paratoluene sulfonic acid ester. All these can be analyzed to a very high degree of sensitivity by GCMS. These are a couple of around 10 or 12 different genotoxic impurities are separated by a suitable column, and we were able to do this in less than 15 minutes time. And if standards are available, we can quantify them. So that's the power of a GCMS system. And another type of genotoxic impurity is alkyl halides. We can see here almost 18 to 19 alkyl halides are separated within about 10 to 12 minutes time. And individually, you can see, you can even go for quantification provided the standards are available. Another recent development, especially of interest to pharmaceutical people and pharmaceutical students, are the nitrosamines in some of the latest development pharmaceutical industry. Everybody is now working on this. Some of the certain groups of drugs and other, and they have found the presence of some nitrosamine. There is a group of around 6 nitrosamines, possible nitrosamines. One two common nitrosamines, N-nitrosodimethylamine and N-nitrosodiethylamine, NDMA and NTEA, and they are found to be carcinogenic compounds. So they are to be identified and very precisely quantified in pharmaceutical drugs, which we can do by a GCMS or an MSMS and with the help of even a headspace sampler. So analysis of nitrosamines by GCMS coupled with a headspace sampler, we can very accurate quantitative analysis can be done for these nitrosamines in pharmaceutical drugs. This is an example, NDMA and NDEA, and right from 2.5 ppb to 10 ppb, we have created a calibration curve also, 2.5 ppb to 10 ppb. And GCMS in biomedicals is a very one of the latest requirement. GCMS is an important tool in neonatal screening for metabolic disorders, especially newborn scanning. Newborn scanning has not become mandatory in our country so far, but in many countries, newborn scanning is mandatory. When a child is born, the child is to be tested for any inborn disorders, metabolic disorders, genetic disorders, so that the treatment can be decided by the physician at a very, very early age, so that any of the complications can be avoided. So for this, what is done is the urine sample from the child is taken, and the urine contains lot of carboxylic acids which are produced inside our body because of different types of body metabolism. And there is a certain carboxylic acid profile for a healthy human being. And if this profile is getting changed, that is an indication that there are certain disorders in that person because of that the profile is getting changed. So we have a system, we have a special software also for this. This is called an IM software, Inborn Errors of Metabolism software. And we have developed a lot of methods for this. So for this, a urine sample from the patient is collected. It is subjected to proper sample preparation and sample cleanup because urine is a biological liquid. It contains a lot of unwanted matrices. They are all to be removed, and the carboxylic acids are to be extracted. They are to be derivatized, and then that is injected into the GCMS system. And then this is, you can see the urine profile of a child, and this data was collected in Japan. This is a sample collected from a child after 3 days of birth. And then this is the profile you are getting from GCMS. Then you have to apply the software, IM software, and automatically identify some of the possible disorders. And then the rest of the thing is to be decided by the physician and what is the type of analysis. And we have supplied these type of systems across India at different major hospitals and testing laboratories. And GCMS has got wonderful applications in food industry, analysis of flavoring compounds, identify and estimate of residual pesticides. As I told you before, whatever we are eating and drinking today, they all contain pesticide residues, very, very low levels. That to be very precisely controlled, very precisely quantified, identified. Can do it by GCMS, or nowadays we even prefer MSMS for that. And determination of residual solvents in even packaging material. That's also a very, very important application, not only in pharmaceutical, not only in food industry, but also in pharmaceutical industry. Analysis of coffee aroma by GCMS, SPM. SPM is another technique known as solid phase micro extraction. You have a sample in a vial, you are heating it, the volatile fragments, the aroma compounds or the flavoring compounds or the fragrance compounds are coming out. You can capture these compounds on a fiber. And these fibers, there are different types of fibers available. And these compounds can be captured, can be absorbed on the fiber. And after some time, the fiber is taken out from the bottle and introduced into the GC injection port. And at the temperature of the injection port, these compounds will get dissolved. It will go to the column, and you can find out what are the aroma compounds. So there are two different types of fibers. You forget about it, all those. And so we can use this technique. It's a very, very useful technique called solid phase micro extraction. And using this technique, you can use different types of aroma compounds, different types of perfumery compounds you can analyze. And this is so many compounds can be separated from coffee aroma, and the fuel compounds are listed here. I mean, there are so many more compounds also come from compounds. It's a very, very complex analysis. Okay. Analysis of pesticides in foods by GCMS. You can see not more than 50, 60 pesticides can be separated, or even more than that. Pesticides can be more number of pesticides can be separated. You have to use the right type of column, the right type of method. You have to optimize lot of conditions, and the wonderful analysis of pesticides in food systems and food products by GCMS. And you can see this, all these compounds can be identified and they can be quantified. We can go to very, very low levels of quantitation. We can go for even ppb level detection or even less than that. GCMS has got wonderful applications in forensic science. The most important application of GCMS in forensic science is identification of drugs of abuse. People who are using steroids when they are taking part in some games like Olympic Games or Asian Games, I mean, whatever it is. I mean, so people try to use an unscrupulous way of boosting your capability, you're enhancing your energy. So nowadays it's mandatory for, that is called the doping test, mandatory for all these athletes to undergo the doping test, and we can find out whether somebody has injected a steroid or hormone into the system to boost their performance. And so these are all available in very, very trace quantities in blood or urine. So that is why you remember that high residue analysis, the system is capable to do that. And analysis of poisonous compounds from a site of crime or even from a dead body, we can find out what are the poisonous chemicals gone inside, which has ultimately resulted in the death of the person. I mean, these are analysis of blood alcohol by GCFID-MS along with the headspace sampler. It's a typical forensic application. When somebody is consuming alcohol, it will come in the blood. By analyzing a small quantity of blood, you can find out whether the person has consumed alcohol and what is the content of alcohol in the blood. So these are typical forensic applications. Anticonvulsant drugs can be analyzed and quantified. And analysis of poisonous chemicals, toxicology screening, stomach content from a human specimen died after an explosion. And we have found out some poisonous chemicals like benzene, styrene inside the stomach. We have taken out the stomach content, we have done some extraction, lot of sample purification, cleanup work we have done, and then finally we have injected the sample and did a library search. We identified what are the poisonous chemicals that are gone inside. ROHS application means ROS means regulation on hazardous substances. There are a lot of carcinogenic compounds that can go into many of the plastic items, electronic items. These are all banned items. For example, PBBs, polybrominate, polybromobiphenyls, then polybromo-diphenyl ethers, and these are all carcinogenic in nature. So their presence is, so there is a lot of regulation for this. That is what is known as ROHS regulation. And these have to be tested. There are different methods of testing that. And GCMS is one among them. For example, PBD is, there can be a lot of isomers. And we can actually do this. A PBD solution is analyzed by GCMS, and so many isomers can be identified, and we can even quantify, provided the standards are available. So we can find out the presence of these compounds in a toy or a plastic material or electronic items. There are a lot of things. GCMS in perfumery and essential oils. Perfumery compounds are very, very complex compounds. You require a high resolution capillary column to separate all those compounds, and qualitative identification only possible only by GCMS. You cannot identify all those separate compounds by normal GC. You need to have an MS detector, and we have specified libraries also for that. You can see this. This is a perfumery 0.2 microliter of a perfume introduced into a 100-meter capillary column. And see, more than 100 compounds are coming, baseline separation. Where are you going to identify all these compounds by a normal GC? Impossible. But we can identify most of these compounds by GCMS, because we have got dedicated libraries also for this. So that's the power of GCMS when it comes to very, very complex multi-component samples and naturally occurring products. And the last slide is matrix. There are different types of matrices you can come across. Some of the samples can be of biological origin. There can be blood sample, urine, or a plant-based sample. They're all biological samples. Then most of the samples are otherwise samples are non-biological, like pharmaceutical products, forensic samples, toxicology samples, food samples, chemicals. Chemicals also include lot of items like environmental samples and polymers and pigments and paint. So many items are. So you can broadly divide into biological or non-biological samples, and we have today capability by GCMS to analyze these different types of samples. Some of the samples are difficult because they need lot of complex sample preparation and cleanup, because we have methods for those also. And there are some of the samples are simple, but today we are capable enough to do this analysis and do an absolute quantification at a very high degree of sensitivity is possible. That's the importance of GCMS. So I think with this, this is the GCMS, the latest GCMS Shimadzu is providing, because we are associated with Shimadzu. And this GCMS QP2020NS, this is the latest GCMS that is a single quarter ball GCMS that we are providing, has got absolutely, it's an excellent system with a very, very high degree of sensitivity. Lot of features are available. I just wanted to show you the picture. That's on the right hand side you see GC, and on the left hand side you see the MS. And the GC is called the 2030 Nexus GC and coupled with 2020 MS. So it's called GCMS QP. QP stands for quadrupole, QP 2020NX. And this is the last slide. And I thank everyone for giving me attention for almost more than 1 hour 45 minutes. And this is my contact day. Any other students or any other students want to contact me directly, you are welcome. My email ID is given, rgrijan@toshvin.com. And my mobile number is also given. If you want, you can note it down at any point of time. Anytime if you want to contact me some more information, you are always welcome. And I thank all the participants. And once again, I thank all the faculty members and all the authorities of Marwadi University for taking a wonderful initiative in conducting this today webinar program. And I hope, as I told you yesterday, the biggest beneficiary, I am 100% confident, will be the student community. So I request all the students to make use of all this information, whatever little information you have received over a period of 2 days, and I feel and I hope it will be useful to you in your curriculum, as well as when you go out of this university and go to a corporate world. Thank you once again. Over to you, sir.
Yes, sir. Mr. R. Girijan, sir, we are very much thankful to you for very insightful and very informative session. Through this webinar, you enlightened the basic concepts behind the gas chromatography as well as mass spectroscopy. Sir, I now would request you to answer the questions asked by the participant.
Yeah.
One question from yesterday's session. One of participant, Dhruv Patel, want to know that sometime previous sample traces remain into next sample. So we used to give methanol washing. So will it affect column efficiency or not?
Absolutely not. See, when you are analyzing some sample, is something remains inside the system, and it is coming in the second sample, which is known as carryover. It is known as carryover. Carryover happens in the case of GCMS. But as far as possible, we have ways and means by which we can actually remove the carryover. So what Mr. Dhruv Patel is doing is also good, because he can give a solvent wash so that whatever is remaining inside the column will come out and it will be washed out and the column will be clean, and it is not going to affect the column or the second sample. It's absolutely good. He is right.
Next question from H.J. Walla. How in-column derivatization is carried out with regarding high molecular weight containing components or samples?
In column derivatization is normally carried out in the case of HPLC, not in the case of GC.
Okay.
In the case of HPLC, there is a provision for post-column derivatization called post-column derivatization or pre-column derivatization. That is normally done in the case of LC, but not in the case of GC. Not in the case of GC.
Yes. One of our participant, Prashant Misra, want to know on what factor it will decide that we should go for electron impact ionization or chemical ionization.
Okay. If your interest is only to identify the compound, you want to know what is the compound that is present in your sample, you go for electron impact ionization. Because once you do an electron impact ionization, you have the freedom to go for library search, and the library will tell you what is that compound. Okay. Now, if you want to know what is the molecular weight of that compound, then only you go for CI. Otherwise, no.
Okay, wonderful, sir. Next question from our senior faculty member, that is Dr. Ashish Kada. He want to know, will fragmentation remain uniform for particular compound if we repeat the operation again and again?
Yep, absolutely, absolutely, it will remain same. If it is going to change, then MS has no validity. So even if I have a sample X molecule, and if I am going to do it multiple times, as far as the compound is same, the fragmentation pattern will remain always same. There will be absolutely no change.
Okay. One more question from Dr. Ashish Kada. Will moisture in sample affect GCMS analysis?
See, moisture as far as possible, I mean, it's a very good question. I mean, understand this, if at all they are doing some GCMS analysis, normally in any vacuum system, water molecules having molecular weight 18, water molecule is 18 molecular weight. Water molecules are the most difficult molecules to be pumped out completely. Even if your pumping system, your vacuum system is very good, complete removal of water molecules is not possible. So even when you do GCMS analysis, once you get a complete vacuum inside, if you go and see the vacuum profile, still you will see three different peaks, residual peaks. One is the maximum height will be 18, that is water molecule. 100% removal is not possible. So, but what we do, so when we are trying to analyze a sample, we need to, many times we have to dissolve the sample in a suitable solvent. Many times samples are soluble in water, soluble in organic solvent. As far as possible, try to dissolve the sample in an organic solvent. What happens if you dissolve the sample in water, it becomes an aqueous solution. And when injecting the sample, you are unnecessarily introducing more amount of water molecules into the system, into the ion source. And that can even reduce the sensitivity. So wherever possible, try to dissolve the sample in an organic solvent and not water. But then, if at all your sample is only soluble in water, then there is no other way. Yes, we have done that. I have done that also. I mean, in that case, dissolve the sample in water, but try to reduce the sample quantity. Try as little as possible. And see that before injecting the sample, see that your vacuum is totally good, so that the effect of water will not be. Otherwise, if you are introducing too much of water, the vacuum level will come down and the quality of mass spectrum will go bad.
Yes, sir. One question asked anonymously, will response from a flame ionization detector affected by change in the mobile phase flow rate?
Mobile phase flow rate will not change the, what is the question, sir? Once again?
Will response from flame ionization detector affected by change in mobile phase flow rate?
No. The response will not change. It does not depend on the flow rate. I can use different flow rates for my sample. The response actually depends upon what is there are certain other ratios also. I mean, what is the hydrogen to air ratio? That's the most important thing. But it definitely does not depend upon the flow rate of the carrier gas. No.
Okay. Sir, I too have one question. Most of the solvent used are halogenated. Is there any specific reason for that, as they are carcinogenic in nature?
What is that, sir? Halogenated samples? What is
solvent? Most of the solvent are halogenated. So is there any specific reason for that?
Effect on what? Effect of this on what?
Most of the solvent
Ah,
to dissolve the sample. Used are halogenated. So what are the
right.
reason behind that?
I mean, maybe because the sample, that depends on sample characteristics. We are also
Yes.
using different times, different halogenated solvents for dissolving the sample. Because, for example, chloroform.
Yes.
Chloroform is a wonderful solvent for many of the compounds. So
Yeah.
we use chemical, but as far as possible, when if there are other solvents available like ethyl acetate or any other solvent that is available, then we
Okay.
prefer that. But in some cases, we need to use a chlorinated solvent because of the solubility of the compound is maximum there. There is no
Yes.
harm in using that. And when you go for actual GCMS analysis, there is solvent cutoff time. We can use that solvent cutoff time to remove that solvent peak from our mass spectrum. So that also is possible. So
Okay,
there is
sir.
there is nothing wrong in that.
Okay, sir. So this is the last question, also from our one of our faculty member, Jayanti Lal Makasana.
Okay.
What parameter we should consider during GCMS or MS method development for analysis of natural product sample?
Natural products means it depends on, first of all, you should identify what are the natural products. Natural products can be different things. Suppose I had my own experience one. Somebody gave us a sample which is natural product plant extract. I mean something which is the extract from the root of a plant. And unfortunately, I mean, according to this was given by a student a couple of years back, and a PhD student, and telling that she was telling me that the sample is a volatile sample, then we tried to introduce the sample to capillary column, but unfortunately, it was a non-volatile sample, and it totally spoiled the column. So first of
Okay.
all, before introducing any natural product, please see from where it has come. Many
Okay.
times the plant extracts are non-volatile samples, they are highly polar samples. So you need to have some sample preparation method, and we have to convert the sample into a volatile form, maybe sometimes by a suitable derivatization method. So you need to have some basic information before analyzing any plant extract, especially in GCMS, GC or GCMS.
Okay, sir. So one more question, sir.
Yeah.
Like when we are going for mass spectroscopy,
Uh,
samples should be free from foreign particle.
hmm.
So, if any foreign particle remain in that sample,
uh.
which component will be affected most?
If foreign particles are present sample, it is not the component that will be affected. It will be the hardware that can be blockage in the injection system. It can block sometimes block the column. It can contaminate sometimes the injection liner, the hardware system. As the
Okay.
sample components are there, there is no effect, but it can sometimes create problems and clogging in some of the hardware system. So as
Yes.
far as possible, before injecting any sample, have a physical examination. It should be a clear sample. If it is not, please try to filter it through a suitable filter.
Yes.
Make it totally particle-free solution. Otherwise, it can create problems in the hardware system.
Yes, sir.
It can
Thank you,
even
sir.
it can even block your syringe. That's also a major problem.
Yes, sir. Yes, sir. Thank you, sir, for a very wonderfully answer. I am very much confident that this webinar would have helped all the participants in better understanding the concept behind the gas chromatography and mass spectroscopy. Once again, I would like to thank you on behalf of Faculty of Pharmacy and Faculty of Science, Marwadi University. Finally, I would like to invite Dr. Vicky Jain, Principal, Faculty of Science, Marwadi University, for concluding remarks and vote of thanks. Sir, over to you.
Yeah, thank you very much, Burman sir. A graceful and warm morning to our most valued guest, come resource person, Mr. R. Girijan, Management Committee, most beloved students, and last but not least, all the participants gathered over here. It is my privilege to have been asked to propose a vote of thanks on this occasion. I, Dr. Vicky Jain, on behalf of Faculty of Pharmacy and Faculty of Science at Marwadi University, first of all, extend my most sincere thanks to Mr. R. Girijan sir, product consultant, Toshvin Analytical Pvt Limited, Mumbai. Our speaker, who spared his valuable time from his busy schedule to conduct a mesmerizing, knowledge-enriching sessions for 2 days. I thank him for providing the entire knowledge of GCMS, starting from basic to advanced theories, and sharing with us your opinion and vast experience. We have been fortunate to have eminent persons from industries, academic, and utility work in the area of separation techniques. And I'm sure that the participants would have been benefited by attending this two-day webinar. Uh, Further, I would like to extend a big thanks to the master of the webinar, Dr. Lalji Baldania sir, for his effort towards organizing webinars with his style and his own ideas of explanation of everything. I also would like to extend our sincere thanks to Chairman, Vice Chairman, Provost, Registrar, Deans, and all the professors of Marwadi University for their cooperation in the webinar organized. Yes, of course, events like this cannot happen overnight. So as the wheel starts rolling weeks ago and requires planning and bird's eye for the detail, here we are fortunate enough to be backed by a team of very dedicated and motivated team of our university who knows their task and very much result oriented. I mentioned my deepest sense of appreciation and would place on record my heartily thanks to Dr. R. Burman and Dr. Yashwansi Jadeja, because of whom we made this event possible. I once again want to state that we are grateful to the renowned speaker. We thank you for being with us and catering knowledge and expertise with these participants. It has been a great pleasure. Last but not the least, I would like to heartily thank the instrumental person, Mr. Falguni Makwana, Territory Manager, who acted as a bridge between Marwadi University and Toshvin Analytical Pvt Limited, and introducing such a renowned resource person. In true sense, we all have enjoyed a lot and acquired knowledge about GCMS from all the dimensions. Thank you very much. Thank you very much, all of you. Thank you.
Thank you, sir. Thank you, sir. Thank you very much.
Yeah.
Thank you, sir, for your kind appreciation. We will share a link for online feedback form through email who have remained present on both the days throughout the session. Therefore, I would request all the participants to fill up the online feedback form. Then only an e-certificate will be issued through email latest by July 19th, 2020. Stay safe, stay healthy, and keep on learning. Thank you. Thank you all.
Thank you, sir.
Thank you so much, sir.
Marwadi University, a place where the library doesn't sleep until you do. Playgrounds that never tire until you run out. Laboratories that continue to innovate with you. An amphitheater that encourages your talent when no one else does. Hostels where you will find rooms for comfort. A placement cell that nurtures and makes you future ready. Classrooms that have its arms open for you. A faculty who is your friend, philosopher, and a guide. A campus that is nothing less than a home for you. A university that will always be focused on your development, your growth, and your success. Feel the positivity. Witness the development. Discover your true potential. Marwadi University. Discover you.
World-class infrastructure, diverse faculty,